Hi everyone. In this video, we're going to look at how we can solve, well, not quite solve, but know something about the solutions of differential equations. And a differential equation is, simply put, an equation that has differentials in it. It can take a lot of forms, and you can have first derivatives in it, second derivatives, so on. We're going to consider a very straightforward differential equation here to start. dy dx equals 3x. So what do we know about the solutions to this equation? Well, we know a bunch of things based on what we know about integration and what we know about derivation. We know that the solutions are going to be quadratic. We know that we're going to have an infinite number of solutions that are all separated by vertical translations. We've talked about this when doing derivatives. We can know even more specifically that basically the solutions to these are antiderivatives of 3x, which actually means we know that in this particular case, they're going to be 3x squared over 2 plus some constant. So we actually can say quite a bit about these differential equations. But what if we don't particularly care about the specifics? We just kind of want to know some sense of the idea of them. Or if it's something that we can't easily anti-derive. Well, that's where slope fields and Euler's method come in. So if we consider this one up here, where we actually do kind of know what's going on, so that I'll draw a slope field of this and we can hopefully sort of interpret. A differential equation allows me to figure out what the slope is at any given x value. Now, I don't know what the y value will be at that x value, but I know what the slope of the function will be. So if I consider here that the slope, so dy dx, is always going to be 3x, when I pick different x values, so I'm going to use a scale that's pretty big here so that I can sort of see what's going on. When I know the x value, I know what the slope is going to be at that x value. So when x equals 0, for example, I know I have a slope of 0. So no matter the y value, this would be the slope of a tangent. So I just draw a bunch of little like horizontal slopes here to show that, okay, I know at those segments, the tangent would be 0, so that's where I'm going to have a vertex. Since I do happen to know that this is a quadratic function, the family of functions are quadratic, I also know that that's where their vertex would be. To give me a better sense of the shape of the rest of the solutions, I can consider what happens at other values of x. So when x equals 1, the slope is 3, so that's going to give me slopes that are positive. And as x gets bigger, those slopes are going to get steeper. So I get steeper as I go. And if x was 3, these would be very steep. Oops, why did I put a 5 there? That doesn't make any sense. They get quite steep as we go. Even steeper still, almost looking vertical at this point. Over towards the other side, I get a symmetrical idea, but the slopes are going to be negative. So -3, they get steeper still, but still negative as I go further out to the left. So I get some sense when I step back and kind of look at the big picture of this, that we can sort of see through here the general shape of flow of curves going like this. And I get a basic idea of what the solutions would look like without necessarily being able to define the specific function or even relation if they aren't functions. So let's consider one that's a little more complicated where we don't just easily know the antiderivative. So here's a slope field given for the differential equation dy dx equals x plus y. So for any given value point on the curve, I know that the slope would have to be the x coordinate plus the y coordinate. So considering, for example, if I'm at the point 0, 0, we're going to have a slope of 0. But even specifically if I have, so you can see we've got this vertical line through here of slopes. Those are all the slopes that are equal to -1. Those would be when the difference between the x and the y value is -1. If x is equal to -y, so along the line x is equal to -y, you're going to get slopes of 0. So if I kind of find that through here, it's not quite perfect right there actually. X equals -y. We've got slopes that are equal to 0. And this sort of gives me a sense overall of what's going on. So again, I can sort of trace that there's solutions that kind of do these things. Or down here, they're maybe looking like that. So I can get a sense of what the overall shapes of the various solutions are. This one isn't quite as simple as going to be a nice, neat function. We will learn how to algebraically figure out the relations that form the solutions to this differential equation, but the slope field gives us a basic idea of tendencies. It also sort of introduces us to this idea of Euler's method. So Euler's method is a way of finding values. If I know a solution on the differential equation, and I'm wanting to use it to approximate a value at a different, for example, in this case, different value of x, but I don't know the actual relations. So usually with 4 or 5 steps, we can approximate things that are close by essentially using straight line approximations. So if I start with the value I'm given, x equals 0 when y equals 1, then I can use this differential equation to find the slope at that point. So 0 plus 1, the slope here is 1. Now, what I'm essentially saying is that if I have this curve doing something, I don't know what it's doing, but let's say this is the point 0, 1, and I'm wanting to figure out what is happening at 0.5. Now, I don't know that this curve is concave up or increasing or anything like that, but the basic idea is I draw a straight line out from this first point, and I find a point that is on that tangent that isn't necessarily on my curve. There's a little bit, but it should be fairly close to the curve if delta x is pretty close. Then I use that, reassess the slope, and keep going from there. Now, there's going to be some divergence because I'm not actually on the point at any given point, or on the curve at any given point, sorry. But it should be close as long as this particular relation that is represented by this differential equation isn't doing something very bizarre. I don't have any guarantees that it isn't doing something bizarre around this point, but it's the best I have right now. So if the slope of that tangent line is 1, then delta y is going to be the slope times delta x. Now delta x in this case, delta x is 0.1, because that is what we are going to go up by each time. So the slope times delta x is just 0.1, which means that my new y value is 0.1 more than my old y value, so 1.1. This now gives me my second point to go through this next process. So the new slope is now 0.1 plus 1.1, so 1.2. And delta y is going to be 1.2 times 0.1, so 0.12. My new y value is therefore going to be that 0.12 plus the old y value of 1.1, so 1.22. So we carry on from that process, just keep doing the same thing basically. So 1.22 plus 2 gives me a new slope of 1.42. When I multiply that by 0.1, we get 0.142, which we add on to the 1.22 that was my old y value, 1.362. That's my new y value. So I'll just kind of zip through these a little bit. So add that to 0.3, 1.662, which gives me 0.1662, which is added on to the 1.362 is going to give me 1.5282, and I just keep doing this until I get to 0.5. I'm actually not going to need this last row in the table at all, because when I get to the end of the fourth row, that will have the right value. 2, so adding that to 2.4, we get 1.9282, which is 0.19282 as a delta y, which when I add it on to 1.5282, we are going to get 1.72102. So a reasonable approximation, let's say, might be 1.7. Now, unless we can actually solve this differential equation, we can't verify whether that's a good approximation or not. But at the moment, based on the information we have, it is the best we can do.